All right, so today we are looking at production of aldehydes and ketones. So let's just sort of frame that problem again. So here's my aldehyde, and a miracle happens. And it's an alcohol. And the miracle, the reducing agent, which you sometimes write as just as an H in square brackets, which just means generic reducing agent without specifying what it is. My reducing agent is going to add some hydrogen. Okay. Let's just think about this molecule here. It's got some polar groups on it. How are those polar groups arranged? What's the organisation of partial charges? You know, we talk about partial charges, don't we? The delta pluses and the delta minuses in a molecule caused by difference of electronegativity. Well, we're up to you. What would be the important partial charges that we'd need to know about in this molecule?
Carbon-oxygen bond.
Carbon-oxygen bond is polarised, yeah. Which way around is it?
Well, towards the oxygen.
So which has the delta plus, which has the delta minus?
The C has the delta plus.
That's right. Okay. So oxygen's more electronegative than carbon, so it takes more than its fair share of the electrons, so it's got a slight negative charge, and carbon's got a slightly positive charge. So I want to add some kind of hydrogen to that carbon. Here it is. Here's my some kind of hydrogen. What kind of hydrogen is going to want to attack that carbon? Ewan, up to you.
Yeah, negative.
A negative one. Okay, great. So that's fine then. So we'll just use H minus then, right? Is that okay with everybody? H minus. Just done an entire topic on acids and bases. We've seen an awful lot of H plus. I don't think we've ever really talked about H minus, have we?
Steal the proton away. Hydrogen.
Steal a proton away. Hydrogen only has one proton, so if you steal it away, you literally have nothing.
With an electron.
You'd have an electron. It's not really an atom anymore, is it? It's just a flick of charge. What's an easier way to make an H minus?
Ooh. You could use gain an electron.
Here's hydrogen. It's got one proton in the nucleus. It's got one electron in orbit, as you just said. If we give it another electron, suddenly that's H minus, isn't it?
How do you do that?
You know, going back to our sort of GCSE view of the world, we remembered that atoms form stable ions by filling their outer shell, right? Well, how many electrons can I get in the outer shell of the first shell? That's 2. So all I've done is form a stable ion by adding an electron to hydrogen. It's just that it's slightly less stable than H+. So if hydrogen has a choice in the matter, it'll form the H+ ion. But there are ways that we can persuade it to take that electron. So if I combine my hydrogen with a very electropositive element like potassium, something that really likes to give electrons away, then that would form potassium hydride, it's called. where the hydride ion, just like the chloride and the nitride and the oxide ion, they're all negatively charged, the hydride ion is H minus. Now, as it happens, potassium hydride is not stuff you really want to work with. If you're using the wrong chemicals, if you mix it up slightly wrongly, think fireball as a way to describe what happens. It's very, very reactive stuff. So those clever people in the research labs have come up with something rather more stable, and that is NaBH4. So sodium, if you go back to your oxidation state rules that we did some time ago, sodium's in group 1, elements in group 1
+1.
always have an oxidation state of +1 in compounds. Same for elements in group 3, they're always +3 in compounds.
Hydrogen's -1.
The overall oxidation state of the compound is 0, so H must be -1. Okay. So that's our form of hydride.
What's it called?
Now, what's it called? Everyone in the chemistry world calls it sodium borohydride, which is nice because it's sort of sodium borohydride, it just tells it as it is. The name is actually sodium tetrahydridoboron 3, which I find a bit of a mouthful. I'm just going to call it NaBH4. Are we all okay with that?
Perfectly fine.
Because if you write NaBH4 in your AQA exam, you'll get the marks. Okay, reduce with NaBH4. Why do we need to call it anything? It's NaBH4, right? We're chemists. We think in terms of symbols. So, hey, NaBH4 it is. All right. Okay. So now we've got our all-important source of hydride ions, our NaBH4. Now, I'm just going to move that over a little bit. Now we can proceed with our new mechanism. Okay, let's go.
Oh, that's me orange.
Orange pen? Anyone? Red pen? No red pen. No orange pen?
Pen there. It's on the floor.
Ah, gravity. Ah, thank you very much. Gotta have your curly arrows in red or orange. Okay. So what's our first line of attack here?
You need a H minus to C.
So what does our curly arrow represent,
Electron
Matthew?
transfer.
How many electrons?
Okay.
Yeah, so the curly arrow, remember, is the movement of a pair of electrons. It's not the movement of the H minus. It's not the movement of a thing or an atom or an ion.
So the electrons are attacking.
The electrons kind of lead the attack. Okay.
This is general.
If the electrons weren't there, then nothing would happen. All right, that's going to leave carbon with a bit of a problem, because if that H forms a new bond with carbon, it'll have 5 bonds. Carbon can't have 5 bonds. So something's got to give. And what gives is that carbon-oxygen double bond is not going to break completely, but one of the double bonds is going to break. So if I just redraw that. So I've now got oxygen with a minus charge on it. That's the original hydrogen that was there already, and that's our new one. So if you were doing this in real life, you get your NaBH4, whatever you want to call it, and you would probably warm it gently and have the reaction bubble away for some time. And when you think that all of the aldehyde has turned into alcohol, you throw in a little bit of dilute acid. So there will be some H plus in there towards the end, but it's like a second step. So if you're confused about how H minus and H plus are sort of sharing a bedroom, they're not. That will be step one, bubble, 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 half an hour, whatever it is. When you think you've got all of your alcohol, then we chuck in a bit of H plus, and hey presto, we can get our alcohol. Okay, which is a sort of weird way of drawing ethanol, sorry, it's ethanol. That's ethanol. Just be careful when you're writing your ethanol and your ethanol that you're very, very clear about that A or O at the end there. Okay, great. So we've got our reagent, which was NaBH4, that's fine. What type of mechanism is this?
Nucleophilic addition.
Someone's been reading the book. Why is it nucleophilic, Matthew?
It's a nucleophile.
What is?
H minus.
Yeah, H minus, because it's negatively charged, is nucleophile, nucleo meaning sort of positive, so positive loving, nucleophile. We don't translate nucleophile as positive loving. If you're asked in the exam what nucleophile means,
Proton donor.
it's definitely not a proton donor, that's an acid.
No.
Last topic, what's a nucleophile? I'm going to go to Aidan for this, because we've kind of gone around the classroom, haven't we? Think about what it's doing.
It sort of seeks a nucleus
No,
or positive charge.
no, that's not what we're going to say in the exam. What's the nucleophile actually doing?
Goes carbon, but it can't be like that.
Remember, the curly arrow shows us the movement of...
Electrons.
Okay.
Donates electrons.
Okay, how many electrons?
2.
So, electron pair donor. Which is not dissimilar from proton donor, so you have to be careful you don't mix those up. So our nucleophile, the H minus, is our electron pair donor. And then what type of mechanism is it in terms of addition? I think you said actually already, didn't you? Remember, elimination is anything that makes a double bond. Addition is anything which breaks a double bond. So because we're starting with a double bond and then it's gone in the end, that counts, not additions, that counts as an addition reaction. Breaking a double bond or replacing a double with a single, if you want to think about it that way. So we've seen electrophilic addition. So this is the nucleophilic addition. You've also seen nucleophilic substitution. So it's important to have all of these clear in your head. Nucleophilic addition. Okay. Well, just like all the other mechanisms, this has some varieties. I can change my nucleophile here. What are some other nucleophiles we know and love? I'm going to go to Alfie for that one. Minus is a good nucleophile. Any more in your little bag of nucleophile? Perfect. That was the one I was going for. I mean, anything with a negative charge, Cl minus, Br minus, will have will be nucleophiles. Are there any nucleophiles anyone knows that doesn't have a negative charge? Okay. By virtue of its lone pair, of course, on the nitrogen, and water would be a good nucleophile as well, although not strong enough to make this reaction happen. I'm going to use Cn minus, so I'm just going to do the whole mechanism again with Cn minus. Of course, not much will change, right? The Cn minus will come in with its lone pair, attack the carbon, form a new bond with the carbon. The electrons will hop from the carbon-oxygen double bond onto the oxygen, and then we'll get to our intermediate here, which will be exactly the same, except instead of a new H there, it'll now have a new Cn there, and we'll have a new Cn there. Okay. All right. So, just a subtle bit of language here. The Cn minus ion is called cyanide. Yeah, something you don't really want to mess with. Yeah, cyanide. That's an ion. That is not. It's not an ion anymore. It's covalently bonded. What's our CN group called when it's
Nitrile.
covalently bonded?
Nitrile.
Nitrile. Okay. Right. How many carbons are in that nitrile? Kieran? 3. Okay. Don't forget that we just added one. So this was ethanal, but this will be. Okay. Be very careful in how you write that. It's not propan-nitrile. It's propane-nitrile. The E counts, AQA, mark for it. And the tendency is to contract that and write propanitrile without the E in the middle. So that's the first important feature of this molecule, is that we have to remember it's got a new carbon in it. We have to remember to write an E in the name. And there's something very exciting about that molecule. Drum roll.
The alcohol.
That's not the exciting thing about it. It was an alcohol before.
Nitrogen.
It's got 4 different groups around the carbon. 3. So one of the things you're going to have to get good at is spotting that. 4 different groups around the carbon means it has optical isomers. Or does it? Because if I do this reaction, if I take some ethanal and I boil it up with potassium cyanide for a bit and blah, 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 get to the end, and then I test my propan-nitrile that I've made, it shows no optical isomerism. Like, test it, I mean, if I put it in a polarimeter, right, and see if it can rotate plane polarized light, it won't. What does that mean? I have a molecule which exhibits optical isomerism, but it doesn't exhibit optical isomerism. I mean, it should do, but I can't see any in the polarimeter.
Is the mixture racemic?
Okay. Remember, if I make a 50-50 mixture of both optical isomers, shows no optical activity. We say it's racemic, or racemic mixture, or a racemate. Remember that word that looks like racemate, but isn't. So what we make is a 50-50 mixture. Okay. So before we go any further, we just need to understand why. Why do we not make one isomer? We make both, and we make both exactly in a 50-50 ratio. Well, in order to understand that, we kind of have to go back to the beginning when the nucleophile first attacks, and we need to take a closer look at this molecule here. If I think about the geometry around that carbon there, you've done a bit of molecular shape, haven't you, in year 12? What would the shape be of just that carbon and the 3 groups around it? What shape would I have there? Where are we up to? Trigonal planar. Okay, so I can imagine a flat plane. Can you explain why it's trigonal planar, Jerry?
Because all of the bones are on the
Because
all the bones are on the same plane.
yeah, but why does it form the?
Like one can be
What was that? I just missed that.
120 degrees between each.
Yes, yeah, that's all. Those are all descriptions of trigonal planar. But why is it trigonal planar? How did you know? How did you work out that it must be trigonal planar?
Forms 3 bonds.
What was it?
It forms 3 bonds.
Right. So you've got 3.
Bonded pairs.
It's not the bonds. It's the electrons in the electrons in the bonds. So you've got 3 groups of bonded electrons,
3 bonded pairs and
and they all
are bonded. So
are all bonded. Yes,
bonding pair.
3 pairs of bonded electrons. Sorry, not 3 pairs. 3 groups of bonded electrons.
No lone pairs.
No lone pairs. And those 3 groups of bonded electrons,
Are different.
I'm looking for the bit you'll put in your answer. So this is if the question is why is it trigonal planar, this is the bit I need in your answer. So 3 groups of bonded electrons, all, does anyone know the 4 words that come at the end of that?
Does it all repel each other?
Repel each other
Like as much as behind?
equally, is the
Oh,
simple word to put it. Yeah, they all repel each other equally. So I've got my H there. Let's not worry too much about that carbon there. Those 3 bonds, and I've tried to sort of draw that on a flat plane, all repel each other equally, which gives us, yeah, as you said, 120 degrees as the bond angle. But the important thing is the whole thing's on a flat plane. Right, so here comes my Cn minus. Dun, 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 dun. Well, it's got a choice now, hasn't it? It can either come at the molecule from the top, or it can kind of come at the molecule from the bottom. I could imagine, it's either going to come in that way, or it's going to come in that way. And, importantly, it's got a 50-50 chance of coming in from the top or the bottom. And if it's got a 50-50 chance of attacking from either side, I'll get a 50-50 mixture of both optical isomers. Let me just write that out. So the molecule is what?
Is it random cell, like it goes from the top or the bottom?
It's random, and because of course we're talking about millions of billions of trillions of reactions. Even a fairly small sample, you've got countless numbers of ethanals. The 2 are going to be pretty much close to 50-50. So there's equal chance of the nucleophile. I'll call it a nucleophile because it doesn't have to be Cn minus. Attacking from either side, so we get a 50-50 mixture. That's a very common question in AQA to explain all of that. And there's lots of chemistry there, isn't it? We've got a mechanism, we've got some structure and bonding, we've got some naming here, propane nitrile, we've got your understanding of optical isomerism and why this has optical isomers, because it's got 4 different groups around a carbon. And then we've got this attack of the nucleophile from both sides. So lots and lots of tasty chemistry in there, lots of things that they can test you on. And no maths, which is often daunting for some chemists who have been really good at maths and have just been breezing along. Logs, yeah, I can do logs, yeah, no trouble. E to the whatever, yeah, that's fine, bring it on. But this can sometimes be the sort of crunch moment, understanding all of that. Because there is a lot of understanding and a lot of learning. Definitely learning.